What specific problem does the proposed method aim to solve in the field of code transformations, and what gap does it address compared to traditional methods?
The proposed method aims to solve the problem of efficiently synthesizing code transformations from input-output examples, addressing the challenges associated with traditional rule-based code transformations, which are often difficult to implement and lack transparency. Unlike traditional methods, which require extensive manual review and debugging, the proposed approach leverages a loopback iteration process that allows the model to introspect on its outputs and self-correct errors, thereby reducing the burden of reviewing every piece of code. This method also provides a more precise transformation generation, compared to directly rewriting code, as evidenced by the higher precision scores of the code the transforms (CTT) approach over the transform the code (TTC) method. Additionally, the approach addresses the issue of handling edge cases, which traditional methods often underexplain, by allowing the model to refine its understanding through multiple iterations. Overall, the method fills the gap of needing a more efficient, transparent, and precise way to generate code transformations while minimizing the need for extensive human oversight.
How does the proposed method for synthesizing code transformations work? Please illustrate step by step, detailing the process from input-output examples to the final execution of the transformation.
The proposed method for synthesizing code transformations begins by presenting 3 input-output code examples to the model, prompting it to describe the underlying transformation in natural language. This description is iterated upon up to 10 times to ensure it adequately covers the transformation, particularly edge cases. Once the model is satisfied with the description, it generates an implementation of the transformation based on the description and the original examples. This generated transform is then executed in a sandboxed environment against 10 input-output examples, including those previously seen. If the transform fails or produces incorrect outputs, the model undergoes an introspection step where it analyzes the failure, using the previous incorrect code and the failing counterexample to refine the transformation, repeating this process up to a maximum of 50 iterations until it works correctly on all examples.
Can you provide a simple yet illustrative example of how the proposed algorithm synthesizes a code transformation, including the transformation of specific input code into output code?
The proposed algorithm synthesizes a code transformation by first presenting 3 input-output code examples to the model, prompting it to describe the underlying transformation in natural language. For instance, if the input code is a simple arithmetic operation like x plus y backward, and the desired output is x, y backward, the model would initially describe the transformation as replace addition with subtraction. It then iterates on this description, refining it to adequately cover edge cases. Once the model is satisfied with the description, it generates an implementation of the transformation, which is then executed in a sandboxed environment against multiple examples. If the implementation fails, the model introspects on the error, analyzes the incorrect output, and iteratively refines the transformation until it successfully produces the correct output for all examples.
What are the theoretical or practical benefits of using the CTT method over the TTC method, especially in terms of efficiency and precision?
The CTT method demonstrates significant theoretical and practical benefits over the TTC method, particularly in terms of efficiency and precision. Specifically, CTT achieves a higher precision score of 0.95 compared to TTC's 0.60, indicating that CTT is more accurate in producing the expected output from transformations. Additionally, CTT synthesizes transforms with an average of 34 lines of code, which is more manageable than the extensive review required for each output in TTC. The iterative introspection and failure analysis steps in CTT enhance its ability to debug and refine code transformations, leading to improved outcomes. Although CTT occasionally misses opportunities for transformation, with a recall of 0.99, its overall performance in comprehending and executing transformations is superior, making it a more efficient choice for code transformation tasks.
How was the method validated or tested in the experiments, and what specific benchmarks and metrics are employed to assess its performance?
The method is validated through a series of experiments comparing the code transformation approach, CTT, against the transform the code approach, TTC. The validation involves synthesizing code transformations from a dataset of 480 input-output Python programs covering 16 transformations, with each transformation evaluated using 30 input-output pairs. Performance is assessed using binary metrics of precision and recall, where precision is defined as the ratio of correct outputs to total outputs, and recall measures the ability to identify applicable transformations. The results indicate that CTT achieves higher precision, 0.95 compared to TTC, 0.60, although it occasionally misses transformation opportunities, reflected in a recall of 0.99 for CTT versus 1.00 for TTC. The experiments also include a failure analysis step, which enhances the efficiency of transform synthesis, demonstrating the importance of introspection in the validation process.
What are the key results achieved by the proposed CTT method, particularly in comparison to the TTC method, and what insights can be drawn from the reported precision and recall values?
The proposed code transformation technique, CTT, achieved a higher precision of 0.95 compared to the transform the code, TTC method, which had a precision of 0.60, indicating that CTT is significantly more accurate in producing correct outputs. However, CTT had a slightly lower recall of 0.99 compared to TTC's perfect recall of 1.00, suggesting that while CTT is precise, it occasionally misses opportunities to apply transformations that could be applicable. The results indicate that CTT excels in understanding and synthesizing transformations from input-output examples, but it struggles with executing those transformations into working code, particularly for more complex optimizations. The average number of attempts required for CTT to synthesize a transform was 1.5 for simple arithmetic transformations and 11.8 for optimization transformations, highlighting the challenges faced in more substantial code changes. Overall, while CTT demonstrates improved precision, the insights suggest that further refinements, possibly through reinforcement learning, could enhance its performance and reduce the gap in recall.